In this snapshot, we will introduce the resistor by way of its current voltage characteristic and see how a fundamental law that we will use throughout the semester, Ohm's law, describes an ideal resistor's current voltage relationship. Resistors hinder the flow of charge. They resist, and thus they can be used to control current. Remember that we mentioned that ideal resistors, if operated within reason, may be modeled as linear elements. Therefore, the current voltage relationship of an ideal resistor may look as follows. The voltage drop across the resistor is plotted on the horizontal axis and has units of volts. The current through the resistor is plotted on the vertical axis and has units, in this case of milliamps, abbreviated with the mA. It takes 1000 milliamps to make 1 amp. Notice that when V is negative, the current is negative. Thus, flip the polarity of the voltage drop across the resistor and the current will change direction. Resistors are passive elements, and the current always travels through a resistor from higher to lower potential. Resistors always absorb power. An ideal resistor has a linear current voltage characteristic. Let's try to fit this characteristic with an equation of a simple line. Recall that y equals mx plus b, where m is the slope of the line and b is the y-intercept. Notice in this case that the y value will be a current and the x value a voltage. Since the line travels through the origin, the y-intercept b is 0. Therefore, we have I equals m times v. What is the slope? Well, simply take one of the points on the line and divide the value of the current by the voltage to find that slope. In this case, the slope is 10 milliamps per volt, or 0.01 amps per volt. Instead of the slope, it's really the inverse of the slope that is the constant used to describe an ideal resistor. Again, in this case, the slope equals 0.01 amps per volt. The inverse of the slope is therefore 100 volts per amp. The inverse of the slope of the current voltage characteristic of a resistor is the resistor's resistance, denoted with an R, with units of volts over amps, or ohms. The ohm is named after a famous German physicist and mathematician. We will abbreviate the unit ohm with the Greek letter omega. So R equals 100 ohms. While we will typically use resistance to characterize a resistor, sometimes we will find it's helpful actually to look at the inverse of resistance, which obviously was the slope of the IV characteristic. The inverse of the resistance is known as conductance and has units of Siemens or Mohs. That's ohm backwards. We now have what we need to define Ohm's law, which mathematically describes the relationship between voltage and current for a resistor. Here we show a common circuit symbol for a resistor along with the current voltage characteristic of a resistor. Notice that the voltage and current are directed such that the resistor obeys the passive convention. Reasonable, as it is indeed a passive element absorbing power rather than supplying it. Here we give Ohm's law. V equals IR. The voltage drop across a resistor is equal to the current through the resistor times the constant of proportionality, the resistance. A very important point should be made here. While we will typically express Ohm's law as V equals IR, current is not the cause of voltage. In fact, it's the other way around, as it's the voltage difference across a resistor which drives current through the element. From a cause and effect perspective at least, writing Ohm's law as I equals V over R is perhaps more meaningful. Now, resistors come in a variety of shapes and sizes. In the lab this semester, we will use typically carbon film resistors. Now, since our hypothetical current voltage characteristic that we've looked at previously described a 100 ohm resistor, let's look at a couple of 100 ohm carbon film resistors. These two resistors have a nominal resistance of 100 ohms and are so-called 5% resistors, meaning their actual resistance will be within 5% of the specified nominal value. Therefore, in this case, the resistance of each resistor should fall within the range of 95 to 105 ohms. Now, why are the resistors of such different size? They have the same resistance. Well, the next video will seek to help explain the performance impact of the different size resistors. And so this concludes our very brief introduction to resistors.